Time-appropriate greetings, everyone. Today, let's look at two examples of paired means. Our first example has 8 random fabrics sampled, and their breaking load was measured under two different conditions, unabraded and abraded. The abrasion here just simulates the fabric wearing out or thinning out. The data I have presented here in the table, for each fabric, its unabraded breaking load and its abraded breaking load. I've also included the difference between the two breaking loads. When this difference is positive, the unabraded or not worn fabrics have a higher breaking load. And also note that in fabrics 6 and 7, the worn out fabric actually had a higher breaking load. That's why the differences here are negative. If we assume that the differences in breaking loads are normally distributed, and we use a significance level of 5%, we ask ourselves, on average, is the breaking load of unabraded fabrics higher than that of abraded fabric? Higher meaning we want unabraded higher than abraded, or the difference between them to be positive. So positive difference. To answer this question, we start by checking that the assumptions and conditions are satisfied. The first assumption is the paired data assumption. Are these data paired? Yes, this assumption is met. How is an unabraded fabric paired with an abraded fabric? So a U-score, an unabraded breaking point, is paired with an abraded breaking point, so an A-score, if and only if they come from the same fabric. A relatively obvious pairing, that an unabraded and an abraded are going to be paired together if they come from the same fabric. Let us check the independence assumption, which is checked as usual by the randomization condition. Are the fabrics independent from each other? Yes, since I stated this in the question that these were 8 randomly selected fabrics. And finally, the nearly normal condition, which verifies the normal population assumption. Can we assume that the differences are normally distributed? Again, this is stated in the question that the differences are normal. And I'll also note that the sample size here is 8. Which is less than 15, so we need this assumption. We need this information. If we didn't know that the differences were normally distributed, this sample size wouldn't be large enough to continue. Let's now state the hypotheses for this test. The null and alternative hypotheses. The null hypothesis is that they're both exactly the same. That is, the average difference between them is 0. There is no difference on average between the two fabric conditions. The alternative hypothesis is the question we want to ask, which was, is the mean difference positive? That was above. Define this parameter in full context. What is mu d? Well, it's a difference. It's a difference in averages. It's a difference in population averages. So it is the population mean difference in breaking load of unabraded fabrics and abraded fabrics. Let's now compute the test statistic for this test. I used a calculator to calculate the average of those 8 differences and the standard deviation of those 8 differences. I encourage you to do the same. The test statistic requires the standard error of the difference, which is just the standard deviation of the difference divided by root n. N being the number of pairs. Standard deviation is 11.86279, and there were 8 pairs. This is equal to 4.1941. The test statistic then is t, d bar minus the hypothesized difference over the standard error. D bar, our sample mean difference, was 7.25. We hypothesize it's 0, that they're exactly the same, and the standard error of the differences is 4.1941. So the test statistic is 1.73. Because this is a t statistic, we also need the degree of freedom to know which t distribution to use. Number of pairs minus 1, n minus 1, 8 minus 1 is 7. So the test statistic is t equals 1.73, degrees of freedom equal to 7. Let's shift over to table t to look up this p-value. We've shifted over to table t. Let's zoom in a bit and head to the 7th row, because we have 7 degrees of freedom. There we go. And we want to look up our t-score of 1.73. And we notice that we have 1.415 and we have 1.895. 1.73 is in between. 1.73 is in between. So we'll come up a bit to our probabilities. This is a one-tailed test, so our p-value is between 0.05 and 0.1. Given our p-value between 0.05 and 0.1, we now need to assess whether this evidence is significant. Remember that we're using a significance level of 0.05. Our p-value, we don't know its exact value, but we know it's between 5 and 10%, which means it's more than 5%. So not significant. Remember, we have too large a p-value. It's too likely. We're not going to reject the null hypothesis. Do not reject the null hypothesis. Do not conclude the alternative. Those are the same thing. If you can't reject the null hypothesis, you can't conclude the alternative. Let's now make a conclusion in full context. The assumptions were met, so let's state that since the assumptions are met, and unfortunately we cannot conclude the alternative hypothesis here. So we cannot conclude at the 5% level of significance Remember, that was because our p-value was bigger than 0.05. And we cannot conclude the alternative. We cannot conclude that the population or true mean breaking load of all unabraded fabrics is higher than that of abraded fabrics. Yes, our sample was 7.25, the average difference, but that difference was too small and the standard deviation was too high, and it's not providing significant evidence at the 5% level. We cannot conclude that there is a difference between unabraded and abraded fabrics with respect to mean breaking load. 9 subjects were each required to complete a task in low light and in high light. Time in seconds was recorded for each performance. So as you can see on the table, Each subject did the task in low light. For example, this person took 26 seconds. And in highlight, this person took 18 seconds. The difference between those two was 7.62 seconds, meaning the low light was higher than the highlight. That makes sense since you might be able to see better in highlight. So the low light task takes longer when it's higher. Do these data provide evidence at the 5% level of significance that, on average, the completion time of this task in low light differs from the completion time of this task in highlight? We'll start, as usual, by checking the assumptions and conditions. First but not least, the paired data assumption. This is met because each low light task and highlight task is going to be paired if they came from the same subject. Each L measurement is paired with an H measurement if and only if the same subject. This is very naturally paired data. Now, is the independence assumption met? i.e., is the randomization condition met? Unfortunately, the question this time doesn't tell us if this is a random sample. So I'll just say that. The question does not indicate a random sample, so may not be met. Well, keep in mind proceed cautiously and note in our conclusion. So we'll hedge our conclusion a little bit to account for the fact that one of these assumptions may not actually be met. The normal population assumption, checked by the nearly normal condition, usually the question might say you can assume that the differences are normally distributed. It didn't say that this time, so I prepared a histogram of the differences. And you can see this histogram, more or less, appears to be symmetric, unimodal, and doesn't seem to have any outliers. So this is a small sample. N equals 9, which is less than 15, so we need a normal distribution. The histogram of differences appears normal. So we'll say it's met. Let's now state the hypotheses for this test and define the parameter in full context. As usual, the parameter for this test is μd, and we're testing if there's a difference between them, aka is the difference between them non-zero. So we're going to assume that they're the same and hopefully conclude that they are different. The parameter is a population mean difference. In task completion time between low and highlight environment of all 2B task doers. So the population of anybody that would be doing this task, what's the difference between their average low light time and their average high light time? That's what μd is measuring. Let's now compute the test statistic for this test. Using a calculator, I found that the average difference was 7.9 and the standard deviation of the differences was 4.150355. The standard error of these differences, SD over root n, is 4.150355 over the square root of 9, which is 1.3835. Then the t-score, d bar minus mu d over the standard error is equal to 7.9 minus 0 over 1.3835, which is 5.71. The degrees of freedom, n minus 1, 9 minus 1 is 8. Let's look up t equals 5.71 and with 8 degrees of freedom in table T. We've returned now to table T. We have 8 degrees of freedom. Zoom in and we notice that 5.71 is off the table. We go up to our p-values, and this is a two-tailed test. So we'll compare it to 0.01, and since it is larger than the largest test statistic, it is smaller than 0.01. It's off the table, it is smaller. It's even further away from the center. With a p-value of less than 0.01, we must now assess, is this evidence significant? Remember that alpha was 0.05. Now, since the p-value is less than 0.01, less than 1%, it's also less than 0.05. It's less than 5%. So it is significant. We reject the null hypothesis, and we conclude the alternative. And we can finally conclude in full context. If the assumptions are met, remember, we don't know if they are. So we need to hedge our conclusion a little bit. We don't know if this was a random sample, and we don't know then that the individuals were independent from each other. But if the assumptions are met, we can conclude at the 5% significance level, since the p-value is less than 0.01, that there is a difference between the population mean task completion times of low light and highlight environments. Our p-value was less than 1%. That's rarer than 5%, my pre-chosen cutoff. So my sample is rare enough to be significant. And using my sample, I conclude that yes, there is a difference between completing this task in high and in low light. Given that we were able to find a significant difference between task completion time in highlight and in low light environments, it makes sense then to estimate exactly how different they are. We do this with a confidence interval, and I'm choosing a 95% confidence interval to complement the 5% significance level that we used for our test. As usual, the confidence interval involves an estimate plus or minus a margin of error, which is the critical value times the standard error. Remember, this is the margin of error. Our estimate for the difference was 7.9. In our sample, on average, the high and low light differed by 7.9 seconds. Plus or minus our critical value times our standard error, which we calculated was 1.3835. Let's go to table T to find the critical value for 8 degrees of freedom and 95% confidence. We're back in table T, and we're still living in the 8th row. We still have degrees of freedom 8. However, we're going to focus instead on the confidence levels here, and we want 95%. We follow this column up to the 8th row, and where they intersect is our critical T star value, 2.306. Now that we know T star, we can fill this in and finish the computation. So the margin of error then is 3.19. 2.306 times 1.38. And I subtract that, I get 4.7. I add it, I get 11.1. So here is my best guess for what the true mean difference is between high and low light task completion environments. I think it's somewhere between 4.7 and 11.1 seconds. Let's now interpret this interval in full context and wrap up this problem. Like the conclusion for the hypothesis test, we need to hedge this interpretation, because this interpretation is only going to be valid if the assumptions are met. If this happened to be a random sample. But if they are, we are 95% confident that the population mean task completion time in low light. Remember, low light was first, so the positive difference means that low light is higher. So we're confident that low light is between 4.7 seconds and 11.1 seconds longer than in highlight. So if you have the lights on, you can go between 4.7 and 11.1 seconds faster than if you have the low light environment.